Block algebra. First thing, the simplest of blocks is the summing junction. We've seen it before, but we didn't really go into mathematics of it too much. But essentially, it takes these signals as inputs and it combines them based on the signs that we put at the arrowheads of the signals. So the sum is, in this case, this one positive added to this one positive added to this one negative. And you can change the signs how you please. So it's a sum of signals. Cascade block diagram is when you have blocks in series along a path. These unidirectional blocks, one input, one output of these blocks, and they're laid out in a series. So if this block had an input and its output goes directly into the next block, then what you can do is use the definition of the transfer function to see what happens with the signals as you pass from block to block. So if you go through the first block, the output x2, for example here, by definition of a transfer function is the transfer function times the input. Right, because G1 was defined as output over input. So you rearrange that and you find x2 is equal to G1 times R. Now if that is your new input to this block and you do it again for this block, go through the mathematics and you'll find that its output is G2 times x2, which is equal to G2 times G1 times R. And you go again and you find that all it's doing is multiplying the transfer functions together. A simple multiplication of transfer functions is involved when you've got blocks in series called cascade. So the overall transfer function is just the multiplication of all the transfer functions together. And that is one of the key things about the Laplace domain that's really useful for control. It enables us to simplify blocks in series by pure multiplication. Remember that you could have had these as differential equations. Each one of these is a differential equation. How are you going to combine the differential equations together? You can't multiply differential equations together. But in the Laplace domain, we get algebraic equations, and if you find them as ratios, then you get multiplication to get the result. Alright, parallel block diagrams. Basically when the blocks are in parallel like this, they share the same input. So R goes into each one of these things. There's a distinct output based on what the block is. So in this case, this one's G1 times R, G2 times R, and G3 times R. The order of the factors does not matter when you're dealing with these single input, single output systems. Okay, so R times G1 or G1 times R, it doesn't matter which way you do it because it is just a ratio, and rational numbers can be multiplied any way you want. So then you add those together and you end up getting this through what the summing junction is. Now you see here I've kind of had arbitrary signal signs, so plus or minus, plus or minus, plus or minus, and then it shows you that the result is plus or minus, plus or minus, plus or minus, right? And you'll find that the total transfer function, remember the transfer function is ratio of output to input. So what I'm finding is the ratio of this output to this input. That's what I call the overall transfer function, yeah? Which is why I go through all this mathematics to see what is this ratio. If I rearrange y over r, it ends up meaning that a parallel system, you just add the transfer functions together. Instead of multiplying, you just add them. Nice simple operation as well. Finally is this one here, which is a really critical one for control, and it might look a bit complicated at first with its algebra, but really it's not, and you'll memorize how to simplify this block diagram before long. So consider a block diagram that has some feedback, really basic feedback, where you have an input signal, you have this feedback signal, they are combined by the summing junction to get a result, which then passes into this forward transfer function in the forward path, so from left to right, to give rise to the output. But the output is being fed back, multiplied by some transfer function to give rise to this feedback signal. And I'm interested in finding the ratio y over r, the total transfer function, given the transfer functions of the blocks within the paths. Well, the first principle way of determining that is just writing out all the equations that appear in that block diagram, similar to what we've just done for the parallel and cascade. So you'd write down what this represents, what's that signal? Let's call it y2. And that y2 of s is equal to, by definition of the transfer function, it's h of s times y of s. And what about y of s? What's that equal to? Well, it's g of s times e of s. Three equations, and I want to reduce it to one equation that relates y and r. And hopefully you can see, just from looking at it, that you can do that by a bit of substitution and rearranging. That's what's going on here. Rearranging and eventually getting this thing here, and then finding the ratio y over r gives you this thing here. G over 1 plus gh is the total transfer function of this. But in general, if it's plus or minus as this feedback signal, then it's g over 1 minus or plus. So that means if it's positive going into here, which we call positive feedback, then it's 1 minus gh. But if it's negative feedback, which is the typical scenario, then it's 1 plus gh. Anytime there's a missing sign, what do we do? Do you think? Assume it's positive, right? I left it out on purpose because we'll assume that all signals into a summing junction are positive unless otherwise noted. Now, one other thing I'd say, negative feedback occurs because of that negative sign here, otherwise it's called positive feedback. What we're doing is finding the combined, or in this case it's called the closed loop transfer function. The closed loop transfer function is the simplification of this block diagram, and we call this product, GH, the open loop transfer function, or loop gain. It's going to be used by Peter Zhu later on. He's going to say, do you remember what the loop gain is? Or the open loop transfer function? And this is what it is. It's what happens if you cut this signal here and measured its output. Because if you cut this, then this disappears here, and you're left with G times H together that R is acting on. R times G times H. R times G times H gives you the transfer function GH. Okay, let's take a look at some additional techniques for simplifying block diagrams that may have an intricate nest of signals and summing junctions. The first one is when you have summing junctions next to each other. So that looks like, as an example of that, I don't have that with me. So for example, you could have, say, a summing junction like this, going into another summing junction like that, and maybe there's two signals going into this one, maybe this one's positive, this one's negative, and then maybe two signals going into this summing junction, both positive. So these can be swapped or combined together, these summing junctions, because the main thing is that the output is just the sum of all the inputs, and we have, in this case, 1, 2, 3 inputs to this whole thing and one output. The summing junction just adds the signals together, so this is equivalent to the same summing junctions but switched in order. Like that. This is identical. It's also identical to putting them all into one summing junction like this. With one output of the summing junction. This might be helpful because there may be a situation where we want to swap these two summing junctions around, because then we could simplify some other aspect of the diagram. And that's simply easy, that's really easy to do. It doesn't matter which way you have them arranged. The next situation is when you have adjacent pickoff points. What's a pickoff point? Let's go back up. Oop, wrong way, this way. This thing here is a pickoff point where we're taking the same signal and feeding it into something else. That's what a pickoff point is. It's a bit like probing some aspect of your circuit or your system to measure something. That's a pickoff point. So if we have adjacent pickoff points, then it would be something like, say, main signal like this. Maybe we've got a pickoff point going this way and a pickoff point going this way to something else. So there's one input in this and there's three outputs, you could say. And that's equivalent to, oh yep, and let's put little dots here to show a pickoff point. This is equivalent to having the pickoff point order reversed. Because clearly, it's just the same signal. The same value exists anywhere along this line. So it doesn't matter whether you arrange it to look like this or like this. They're equivalent things. So I'm saying I can swap these two pickoff points. I'm using a different colored pen so it doesn't look like a signal. I'm just swapping those two bits around. Okay, now I get a little bit more tricky. Moving a pickoff point ahead of a block. So what I want to do is swap this block with this pickoff point. And in the block is a transfer function g between output and input. So say I want to swap these around in my diagram because it will help with something later on. So you can see that there's the pickoff point moved to the left before the block. In order to do that, I need to add g in this feedback path, because this signal here has to be equivalent to this signal here. And for it to be equivalent after the swap means I needed to multiply, put g in the path, put the transfer function g in the path. You see that just from trying to preserve what the signals mean. You can't change what the signals mean when you do a block diagram manipulation. You can only change the topology of that diagram. Okay. Next thing I'm going to do is move a pickoff point behind a block instead of ahead of it. You see, I said ahead of it because I'm putting it further upstream. So it picks off from x1 instead of x2. Now I'm going to make it downstream. I'm going to swap this pickoff point with this block So it looks like this, block and then pick-off point. But to do that and preserve this signal, x2, I need to divide by g. And you can just check that it makes sense, because if you follow this path, x1 to g to 1 over g, you get the right signal again, x1, as it was over here. So it's all based on first principles, these little techniques, but you'll remember them in your head as just swapping them and then multiplying or dividing by a transfer function. The next one, moving a summing junction, this guy here, ahead of a block. So I want to move it over to here. So you see I've switched the summing junction upstream of the block. The summing junction had more than one input. There was this one and this one. So to get the correct output of the summing junction, I needed to put 1 over g in this path. Because then x2 divided by g gets added to x1 multiplied by g to give x3 again. This signal should be the same as this signal. If you're not sure, check it out. What does this signal equal? Well, it's g times x1. And then you add it to x2, so the result, x3, is equal to g times x1 plus or minus x2, because there's a plus or minus here. And then check this one out. It's x1 plus or minus 1 over g times x2, and then multiplied the whole thing by g. Multiply that out, you should get this. So finally, we want to swap the summing junction in the block, but this time we'll make the summing junction downstream of the block. And there you have it here. That multiplies this input by g instead of dividing by g. So there is a pattern to all this, and you could just remember first principles and then figure out every problem based on how it looks, or you could remember these rules and then apply them when you need to. The one rule you won't see in here is the swapping of a summing junction and a block. Oh, sorry, a summing junction and a pickoff point. So for example, here's a block G, and let's say there was a pickoff point here which went to some feedback. There is no rule, no easy rule anyway, that can swap these two things around. So am I doing this right? Summing junction. No, okay. Let's get this right. Here we go. Here we go. Summing junction and pickoff point. Right. Summing junction is here. So we need another signal to it, like that one. So two signals, for example, going together in a summing junction. There's no easy way of swapping the order of that summing junction and pickoff point around. You might be able to figure one out, but it's going to usually complicate the diagram rather than simplify it, so we don't usually have a rule like this. Okay, let's give this a go. A really simple problem to start with. Find the closed loop transfer function of this block diagram. In other words, reduce it to a single transfer function, y of s over r of s. What is the transfer function? Give it a go. It's relatively easy. It doesn't even use these complicated rules that I just mentioned, just the simpler ones. Yeah. Can they cross each other? As long as in your diagram you're clear that they don't actually touch each other, you could put like a little... I have seen this, and in Simulink you can do this kind of thing as well. You can have signals that cross each other as long as you make it very clear that they're not touching. If they do touch, then how do we know it's not the same signal through all these parts? Lob helps as well. But, yep. as a way of showing what you're doing. Like a bit of solder. Get the joint. It might help to label these things as some variable functions like g1, g2, and this one h. And then do the algebra with those variables rather than with the transfer functions, because it gets a bit messy when you have rational functions flying around everywhere. Now, if you've done that, take a look at the next page, and then we get into more complicated block diagram algebra examples. So there's always a test question, test one question on block algebra. And there's usually an exam question with some aspect of block algebra in it. When I asked students last year what were the most difficult concepts of a list, in my part anyway, many did put block algebra because they couldn't get their head around the different rules and how they work. A bit of practice will help. So a good amount of working for this is to show whatever you can diagrammatically in your simplifications and then jump into using equations. And you have to figure out at what point do you jump over to the algebra based on how complex the problem is. So I would say that perhaps I could have one step here which combines these two blocks together because they're in cascade, they're in series. If you combine those together first, then it would look like a simple closed loop transfer function. So I'll combine G1 and G2 together. Because they're in series, you just multiply them together, so you get G1, G2. R was the input and Y was the output. And you have a feedback of H. Make sure you've got arrowheads everywhere, and make sure that you have circles for summing junctions. Don't do this. I've seen this plenty of times. Where it's a block, and then there's a block, and it's like, what's going on here? This signal goes into this one somehow. Yeah, so try to put this summing junction in there. So now we can combine the whole thing into one transfer function using the rule. So I'm looking for y of s over r of s. The output on the right-hand side to the input on the left-hand side. In the formula, it's given as g over 1 plus gh. I'm putting it in quotes because I might be using different variables. But that's what I remember as the formula, where g is the forward path transfer function, which in this case is g1, g2, and h is the feedback transfer function, which is h still, so it's 1 plus g1, g2, h. Now you have to be careful because this could be a minus if this was a plus. People get tripped up that way quite often. Because this is a minus, this is a plus. So that was easy because I've used variables g1, g2, and h, and now I'm substituting them in. The actual transfer functions, 3s over s minus 2 over 1 plus 3 times this thing, so it's 3 times 2 times 3s, which is 18s over s plus 1, s plus 2. Right? Because g1, g2 is on the top and it appears here in the bottom. So I multiply this out, 6s over s plus 1, s minus 2, and I'm multiplying it by 3, which is h. I'll then multiply and divide both sides by s plus 1, s minus 2, and get left with 6s on the top, because the s plus 1, s minus 2 cancel with what I'm multiplying it by, and then s plus 1, s plus 2 is going to cancel with this part, and I'm going to be left with s plus 1, s plus 2 plus 18s. So what I did was simple algebra stuff here. S plus 1, s minus 2, multiplied it and divided. Numerator and denominator, get rid of this fraction over a fraction. And last, don't leave it as this because it's not fully simplified. 6s over, expanded out, s squared plus 1, 3s plus 18 is 21s plus 2. Did other people get this? Oh, okay, thank you. Yep, that's spotted my error here. That should be a minus, and that's a minus. Thank you. S minus 2, s minus 2, which means that's minus 2 plus 1 is negative 1, plus 18 is 17. Right? Did everyone get that? S squared plus 17s minus 2. And that's the single transfer function for this entire block diagram as the ratio output to input. You could also leave it in a factorized form. If you found the roots of this and factorize it, that's an okay way of leaving the solution as well, but don't leave it like this, where it's some factored part plus an extra part. Any questions? Algebra stuff with rational functions. Hey, what happened there? Go. Okay, here, a couple more examples where we get to use some of the more interesting rules. All right, so this example has just g1, g2, g3, g4 nice variables to work with rather than the transfer functions themselves. And what do we have here? Looks like there's only one input, xi, on the left, and one output, xo, on the right. Good thing, determine number of inputs and outputs we have available. So only one of each at the moment. That's cool. So what we're looking for is, as a final answer, we're looking for xo of s over xi of s. So we need a bit of block algebra to actually simplify this. I mean, we could write all the equations down that this represents, first principles approach, but you'd have a ton of equations and you'd probably make mistakes. It's far easier to simplify the diagram first and then only use equations when you need to. That's my general advice. So how do we simplify this? Well, you first look for inner loops or objects that you can simplify first before you go into the outer ones. So I notice that between here and here, this stuff is all alone. We don't have any other signals pulling out of that. So let's simplify this part first,
before simplifying the rest. Now those two signals here are in parallel. They share the same input over here. So therefore they're in parallel, and we can just add the transfer functions together. G3 plus G4. These are themselves possibly some rational functions of S. Then I notice that between here and here, we can simplify things. These are in series like the problem we just did, so we can multiply those two blocks together. G2 times G3 plus G4. Then we notice that between here and here, we've got a combination of just one block in series with this thing, which we could turn into a block using our simple feedback rule of G over 1 plus GH. Now the H in here is just the number 1. This feedback path has a gain of 1. In other words, it's not affected at all. Feedback transfer function is 1. So you apply the rule G over 1 plus GH to this and get this thing here. Then you can combine it because these are in series, and you're left with this, which is the answer that we want. The transfer function between XO and XI. Transfer function is always between a certain input-output pair. Questions? All right, next step, a little bit more difficult. This transfer function has, this block diagram does have transfer functions in it. K alone is just a gain in this case. I guess it could be a transfer function, but we're going to treat it as a gain. It's just a number that we put in here, like 2 or 5 or 2.6. And what's involved? There's a summing junction with one negative signal. Remember, any signal that's not labeled is a positive, like these two are both positive. That summing junction goes into that one, then a gain, and then, it goes into another summing junction with this, which we've seen before. This is how we introduce disturbances within a block diagram, by some additive signal coming from somewhere else. And goes into a block, and then the output of that goes into a block, and then the result is fed back, which goes into the first summing junction. So this system has 2 inputs and 1 output. Even though this signal doesn't come from the left, it's still an input. So Xi and D are inputs and XO is an output. We need to know between which pair we're trying to find a transfer function for. Is it between Xi and XO or D and XO? Well, we're told to find XO over D. So D is the input, and that's our output of interest. We could have found XO over XI, but we're not doing it in this example. That's the standard one you get more familiar with. The one on the right is the output, and the one on the left is the input. Nice standard pair, but it could be any input. Just like there could be any output. There could be multiple outputs of the system. In fact, I could pull this one off and call that an output. You can call that x2. Then I could find the ratio x2 to d, or x2 to xi. All kinds of different combinations we can do based on what inputs and outputs we're interested in. Okay, let me get rid of some of this extra stuff that is not a part of this example. All right, so given that, how do we simplify it? Well, first of all, we need to know how do we treat this extra input over here, which is not part of our problem. You can always assume that extra inputs are 0 unless indicated. I've added the word note always in the notes, which you can add to your notes there. Because this applies to any situation, not just this example. So that means we can ignore that one, or set it to 0. But this whole thing doesn't kind of match what we're used to. So what I suggest as a first step is just twist the diagram around until the input you want is on the left and the output you want is on the right. And that's what I'm doing in this next step. It's just redrawing it so that the input's on the left. Can you see everything else is still in place? I haven't Oh, I did simplify just those two blocks in series in cascade. So it's 1 over s plus 1 squared. But the rest is the same. XO is the result of those two blocks. And then you have feedback that goes into 1 over s plus 1. And then the output of that goes into the summing junction as negative. And then you've got the reference, or another input here. The result of that goes into the gain, goes into the summing junction. So now it's in a more useful form, perhaps, for simplifying. And then what we do is we set this to 0, this input, which means this signal is negative, goes into a summing junction with 0. So the result is just the negative of that signal. So another way of writing this is just to put, well, go back, just to put an arrow here and change this block to negative k. It's equivalent to this stuff here. Because what this does is it takes the negative of that input signal and it adds it to 0. So this thing here, this signal is negative that signal, which is equivalent to if it was a positive signal and we multiplied it by negative 1 to change its sign. And then I can combine the negative 1 with the k, because they're in series, and left with negative k as a gain. All right? So a few steps there, I suppose, in thinking. But that's the equivalent of it. And that's what I apply in the next stage here. I'm just multiplying that negative k that I've just lost with this thing here, 1 over s plus 1, to arrive at negative k over s plus 1. And now it's in a more normal form to simplify using g over 1 plus gh, except note that that's not negative going into this summing junction, so I have to use g over 1 minus gh as my formula. Between output XO and input D. So it looks like this. Questions? No? Okay, next one. What's happening here? There's only one input, one output, so I'm looking for XO over XI. What do I have here? These are all pickoff points which could have been combined together, and here we have summing junctions which could be combined together because they just fall one after the other. So there's a lot of stuff being fed back in all these three paths, and G2, G3, G4 are the feedback transfer functions. So my step is to actually combine those feedback signals together. So just to be clear, what I've done is combine these summing junctions together. So it looks like plus, minus, minus, giving me the result, this one here. And they're in parallel, so I can add or subtract the transfer functions together according to the sign of the signal going into the summing junction. So the positive feedback one was G4. Did I do that right? There's one more. Plus, that's coming from G4. Plus. Plus, minus, minus. So this is plus G4, and then minus G2 minus G3. Combined together in positive feedback. So it's a plus. So that I can then just use G1 as the G, and G4 minus G2 minus G3 as the H, and use the formula and get that output, that answer. Okay, questions about that? Yep.
You've got 1 plus all of that. So when you simplify it becomes a positive summing junction.
Oh yeah, so what in fact I did is I changed this to negative, and then I made the whole thing negative, which does the same thing. Yeah, but good point, because someone else was going to probably ask me that same question. Look at this and go, hey, that doesn't look like what you should be using. You see these things are change sign as well. It does remind me of what a student asked me straight after this lecture last year. So it's a good thing you asked. Okay, and then the next example. This one a little bit more interesting and certainly test level type of question. What makes it interesting is that this pickoff point between G2 and G3 comes back as feedback, and that interrupts the feedback that exists in the other loop. You see this thing is interrupted by this pickoff point. So I can't just try to reduce this thing on its own because it's not separate from the rest. Or I couldn't just try to simplify this part on its own because it's connected to this upper part. So what do? I've got to use those more interesting rules about moving pickoff points in blocks or summing junctions in blocks. And that's what I've done here in this step. I'm moving this pickoff point behind this block in order to unravel this mess of feedback paths. Moving this to here. By the way, there are many ways of solving each of these problems depending on what you move first and second. It's a bit like solving the Rubik's Cube. So if you did it slightly differently than me, that's fine. It's probably okay as long as you didn't try to move summing junctions and pickoff points, which I said avoid. As long as you're moving pickoff points and blocks, in summing junctions and blocks, you're probably okay. So I'm moving that over to here, which means I need to divide by what I'm moving it ahead of in the feedback path. So it's G5 over G3 coming off here. And now, what did I do in the next step if I remember it? No. Oh yeah, in the next step, I am noticing that between here and here, essentially, is this nice feedback path, feedback transfer function that I can find, where the forward path is G2, G3, and the backwards path, or reverse path, is G4, the feedback path. So this is your G, this is your H. In the formula, G over 1 plus GH. Oh yeah. I guess I combine these in series first. That's a pretty easy step now. And then I did something differently. All right, well, there are two ways to solve it. Like I said, you could look at that and simplify this first. But what I've actually done is move this summing junction over to here. This one over to here to combine it with this one. And when I did that, I needed to divide by G1 in this for this transfer function. Look at the rules if you're not sure. Then I noticed that there are two feedback paths that can be combined because they are in parallel. So turn it into one feedback path. And this time I'm preserving the fact that it's negative feedback. So what I'm doing is adding these two blocks together and keep the negative of them. Then I'm applying the standard rule, G over 1 plus GH. Yeah, questions? Nope. Okay, next one. What's interesting about this one? The fact that this one doesn't have a transfer function in it, but if it doesn't, you know that it always represents just the number 1. So that you can combine it with this one because they're in parallel and add it together. So it's 1 plus 3 over S, which is 3 plus S over S. And then the other thing is this guy here, which looks a bit backwards because you go, hang on, I'm used to seeing something like this out the front, so like this one is here. I'm used to seeing a summing junction and then feedback, and this is a summing junction and feedback this way. Seems a bit backwards. But don't get fooled. All you have to remember is that between here and here is that you have a simple feedback where the feedback transfer function is 1, and you just combine these two together using g over 1 minus gh, because it's positive feedback. So that's what I'm doing at this step here. I am simplifying this thing into this. S is g, and 1 is h. To get this. Most of the other steps I've skipped are just when the blocks are in series, it can be multiplied together. Then you just combine them together again, and then use the rule and use the function, the formula, and get this equation as the output. Here is a really difficult one, which I've said is beyond the scope of what I'd test you on, 2 asterisks, but worth trying at some point to test yourself. See if you can solve this without looking at the answers that are given. There are many ways to solve it. Good little puzzle.